Bismillah ar-Rahman ar-Rahim. In the name of Allah, the most gracious, the most merciful. Assalamu alaikum wa rahmatullah. The subject of this series of lectures is topographic maps. It consists of 3 parts. Part 1 gives general outlines of topographic maps. Part 2 demonstrates manual drawing of topographic maps, and Part 3 deals with computer drawing of topographic maps. Manual map drawing. Exercise. A hypothetical map in which the locations and elevations of a number of points are indicated is shown in the figure. It is required to draw a topographic map using a contour interval of 5 meters. As may be noticed from the map, in addition to the bar scale, a ratio scale of 1 to 20,000 are given, and the direction of the north is indicated. All elevations are assumed in meters above sea level. The highest point is 104 meters, located northeast the map. The lowest point is 19 meters, located southwest the map. Thus, the relief is 85 meters. The elevations of the contour lines which are expected to be drawn lie between 20 meters and 100 meters on 5 meters interval. Since a contour line connects points of equal elevation, then the first step in drawing contour lines is to determine the locations of points whose values coincide with the value of any of the contour lines. On examining the map, one can see that the values of many of the given points, which are shown circled, coincide with the value of one of the contour lines. However, additional secondary points whose values coincide with those of the contour lines are required in order to draw a proper contour map. The locations of such points may be determined by interpolation. It is to be noted that interpolation between some pairs of adjacent points may be very simple, such as between the 44 meters and 36 meters, where the 40 meters point located midway between them. Other pairs of such points are shown on the map. Nevertheless, the difficulty arises when the locations of 2 or more contour lines pass between 2 adjacent points cannot easily be determined. Few pairs of such points are shown on the map. In such cases, to determine locations of additional secondary points through which contour lines pass, one may use either a subjective approach or an objective method. The subjective approach depends on estimation, that is to say, it is based on personal feeling, opinion, and ultimately judgment, and which usually involves trial and error, whereas the objective method is based on mathematics. The trial and error procedure usually involves a number of attempts, as the one shown on the map between the points 81 meters and 67 meters, where unacceptable segmentation has been made in the first trial. However, after a number of trials, segmentation that may be considered appropriate was achieved, as shown below. For a beginner, as well as for a person looking for an objective method for manual drawing of maps, a simple mathematical approach that will be explained in some details may be followed. Though its procedures may be considered tedious and take some time, it is theoretically more exact than the subjective method. In the following several minutes, a detailed explanation will be given about the mathematical approach of interpolation. Then, we shall continue the manual drawing. Mathematical method of interpolation. Mathematically, the exact location of an interpolated point P of known elevation depends upon the elevations and the distance between the primary points. Suppose we have 2 primary points, say A and B, among other points, separated by a distance D, as shown in figure 1. It is required to find the distance d between the primary point A and a secondary point P through which a contour line passes. Let see figure 2. Capital D equals map distance between A and B in millimeters. Small d equals map distance, which is to be determined between primary point A and the preceding contour passing through P in millimeters. Capital H sub 2 equals elevation of primary point A in meters. Capital H sub 1 elevation of primary point B in meters. Capital H equals capital H sub 2 minus capital H sub 1 is the difference in elevations between points A and B in meters. Small h equals the difference in elevations between the highest primary point A and the preceding contour passing through P in meters. From trigonometry, small d over capital D equals small h over capital H, or small d equals small h times capital D over capital H. Now, since capital D can be measured from the map by a ruler, capital H and small h are known, then the unknown distance small d from point A to the secondary point P through which the contour line passes may be determined by equation 1. Suppose we want to locate two or more secondary points whose elevations are known between the primary points A and B. That is to say, two or more contour lines passing between A and B through points P, figure 3. Thus, let see figure 4. Small h sub 1 equals difference in elevations between primary point A and the first preceding contour line P sub 1 in meters. Small h sub 2 equals difference in elevations between secondary point P sub 1 and the second preceding contour line P sub 2 in meters. That is to say, equals contour interval. Small h sub 3 equals difference in elevations between secondary point P sub 2 and the third preceding contour line P sub 3 in meters. That is to say, it is equal to the contour interval. Small d sub 1 equals map distance, which is to be determined between the higher primary point A and first preceding contour line passing through P sub 1 in millimeters. Small d sub 2 equals map distance, which is to be determined between secondary point P sub 1 and second preceding contour line passing through P sub 2 in millimeters. That is to say, corresponding to contour interval. D sub 3 equals map distance, which is to be determined between secondary point P sub 2 and third preceding contour line passing through P sub 3 in millimeters. That is to say, corresponding to contour interval. The other symbols are same as before. From trigonometry, small d sub 1 over small h sub 1 equals small d sub 2 over small h sub 2 equals small d sub 3 over small h sub 3 equals capital D over capital H. The proportionality between small d sub 1 and small h sub 1 corresponds to that between capital D and capital H. And since capital D, capital H, and small h sub 1 are known, then small d sub 1 may be determined from small d sub 1 equals small h sub 1 times capital D over capital H. Likewise, small d sub 2 equals small h sub 2 times capital D over capital H, and small d sub 3 equals small h sub 3 times capital D over capital H. Similarly, if there are more than 3 contour lines passing between the primary points, then additional distances are necessary. Small d sub 4, small d sub 5, etc. corresponding to heights small h sub 4, small h sub 5, etc. until the number of interpolated points complies with the number of contour lines passing between the two primary points. Note again that small d sub 2, small d sub 3, etc. are equal to each other and correspond to the contour interval. Moreover, small h sub 2, small h sub 3, etc. are equal to each other and equal to the contour interval. Thus, by replacing small h sub 2, small h sub 3, etc. by the contour interval, equations 3 to 5 may be generalized as small d sub I equals small h sub I times capital D over capital H, which is equal to contour interval times capital D over capital H, where small I is an integer greater than 1. Small d sub I is the map distance, which is unknown, between small p sub I minus 1 and the preceding contour line passing through the point p sub I in millimeters. Small h sub I is the difference in elevations between the point p sub I minus 1 and the preceding contour line passing through the point p sub I, which is equal to the contour interval in meters. Note that all the above equations are applicable if the dimensions of capital H sub 2, capital H sub 1, capital H, the contour interval, and small h sub 1, small h sub 2, etc. are taken in feet instead of meters. The following demonstration illustrates the method of interpolation between few pairs of points in the exercise. Now, after connecting the highest 104 meters point with its surrounding adjacent points, we are going to determine by interpolation the locations of secondary points around it through which contour line pass. So let's start with the 104 meters point and the 71 meters point. So the distance here is 42.5 millimeters. So I have D equals 42.5 millimeters. Now H, which is the difference between these 2 points, is 104 minus 71, which is equals to 33 meters. Small h1, which is the difference between this point and the first preceding contour line, which is 100, is 104 minus 100, and that is 4 meters. Now the contour lines that expect to pass between these points are the 195, 90, 85, 80, 75, and finally the major point 71. So DI, which is equals to the contour interval, which is 5 times the spacing D over H. So we'll start with D1. Here D1 equals 4, which is H1, times the spacing D 42.5 over the capital H, which is 33, and this equals to 5.15, well, let's say 5.2 millimeters, and DI equals 5 times 42.5 over 33, and that's equal to 6.4 millimeters. I have already did the calculations to spare time. So hence D2 equals D3 equals D6 equals 6.4 millimeters. Now I'm going to locate these points. The first point, as we said, is 5.2 millimeters. So from the 104, here, this is 5.2 millimeters. Then I got 6.4. So this is 6.4, again another 6.4, and so on until I reach the last one. Notice that the difference between 75 and 71 is 4 again. So this distance here must equal this distance, and we can easily see that it should be 5.2 millimeters, and if I measure it, it is 5.2 millimeters. Okay, now let's switch to another point, which is the 65 meter. So the distance between the 104 and 65 meters is 53 millimeters. Now, the contour lines that expected to pass from here are 195, 90, 85, 80, 75, 70, and finally 65. So here we have the spacing D equals, as we say, 53 millimeters. H, which is the difference between 104 and 65, equals 39 meters, and H1 again equals 4 meters, and the contour interval equals 5 meters. So D1 equals 4 times 53 over 39. That is to say, it's contour interval, the H1 times the spacing over the difference in elevation. And this gives a value of, let's see the calculations, 5.4 millimeters. DI equals 5 times 53 over 39, and this gives 6.8 millimeters. So D2 equals D3 equals D7 equals 6.8 millimeters. So I start with D1, and as we said, D1 is 5.4 millimeters, and it is from here, it is 5.4 millimeters. Then I got 6.8 millimeters, 6.8 millimeters, another 6.8, another 6.8, until I reach the final 65. So I got the locations, and in the same way interpolation may be made between the 104 points and the other surrounding points. Now one may switch to another point and connect it with the surrounding adjacent points determined by interpolation the locations of other secondary points through which contour line passes. We'll take, for example, these points 78 and 61. Here the distance is 39 millimeters. So I got 39 for capital D, Again, it is, check it, 39. Okay, so capital D equals 39 millimeters. Capital H, which is the difference between 78 minus 61, which gives 17 meters. Small h1, which is 78 minus 75, equals 3 meters. And the contour interval as before, 5 meters. So what I got D1 equals 3 times 39. This is 3 h1 times 39, the spacing, over capital H, which is 17, and this gives 6.9 millimeters. Then DI, which is equals to D2 and D3 in this case, DI equals the contour interval 5 times 39 over 17, and this gives 11.5 millimeters. So I got D2 equals D3 equals 11.5 millimeters, and D1 equals 6.9. So I start with the 6.9. This is 6.9, and then I got 11.5. So it is 11.5, then another 11.5, this is the 75, this is the 70, and this another 11.5, which reach 65, and here we have the rest, which is the spacing, which is about 9 millimeters, is the difference between 65 and 61. So if we write here 4 times 39 over 17, this should give 9 millimeters. So it is 4 times 39 equals divided by 17 equals, which is 9.1 millimeters, almost the same, which is, yes, it is a bit more than 9 millimeters. So it's okay. We can choose another 2 points, which is much simpler. The 59 and 51. The contour line which passed between them is the 55. The difference between 59 and 55 is 4, and the difference between 55 and 51 is 4 again. So this point, which is the 55, must be midway between the two. So we just measure the distance between them, divided by 2, and locate the point midway between them, which is, this is 17 millimeters. So at 8.5 millimeters, which is the midway distance, this point must be the 55. So this process is repeated until all possible secondary points through which contour line pass are located. After this last step of locating all other possible points, we are going to get something like this. It is a map, looks like a spider web, or in fact it is distorted spider web.
Having explained the mathematical approach of interpolation and illustrated its application on few pairs of points, let us continue the manual drawing of the map. Let us determine the locations of secondary points between the highest 104 meters point and each of its adjacent surrounding points. Then move to another high point and connect it with nearby point to find more secondary points, and so on. Use a faint pencil in drawing the connecting lines since you can easily erase it later on. The process of locating secondary points through which contour lines pass is continued until the whole map is covered. As a result, the map becomes look like a distorted spider web as shown in the last of the following sequence of figures. The next step is to connect points of equal elevations by contour lines. Starting with the highest points, it is customary to draw a few contour lines of successive values simultaneously. This will help drawing the contours conformably with the gradual curving, convergence, and divergence, if any, between them. A suitable place on each contour line is chosen to write its value. Remind you again to use a pencil in drawing since it can be easily erased. The red color pencil was used here in drawing the contour lines for illustration. The following set of figures shows successive stages of connecting the interpolated points to draw the topographic contour lines. The final step is to make minor adjustments and smoothing to get the best conformity, consistency, and gradualism between the contour lines. This process may necessitate, in some locations, slightly deviating the contour lines from few of the predetermined locations of the secondary points. Accordingly, reassessment, wherever necessary, is made to the locations of the interpolated points to ensure smoothness and conformity. Consideration is generally given to the relative distances between pairs of primary points amid which the secondary points are interpolated and the elevations of the other nearby primary points. Thus, for example, when two primary points are in the same general direction and located at different distances from a third primary point, such as the sets 88 and 77, 93 and 77, or 81 and 72 from the 104-meter point, see adjacent figure, a greater weight is usually given to the closer points than to the distant ones. In the final stage of contouring, the subjective aspect and experience play an important role to achieve drawing an appropriate map. The following few figures show adjustment and smoothing of the contour lines and the final contour map. Profile drawing. In topographic maps, the profile is a two-dimensional graph that reflects the outline of the Earth's surface between few successive points on a topographic map. In the following illustration, drawing of a profile between 2 points on a topographic map is presented. 1. Select any 2 points between which a profile is required, say X and Y, figure 5. 2. Put an edge of a paper along the line connecting X and Y and mark their locations on the paper. 3. Mark the points of intersection of the contour lines with the paper edge and write down their values. Figure 6. 4. Remove the paper, then overlies its edge on a graph paper. Mark down the points X and Y and the points of the contour lines intersection together with their values. Figure 7. 5. From the points X and Y on the graph paper, erect upward 2 vertical lines to represent the elevation of the Earth's surface, and put centimeters mark on both vertical lines. Figure 8. Choose an appropriate elevation above sea level datum whose value suits the values of the contour lines. In this example, since the minimum elevation is slightly below 30 meters and the maximum is slightly above 100 meters, the sea level datum, that is to say 0 meter elevation, was considered. Note that you may choose up to 20 meters datum level in this example. Mark off the values of the elevations to represent an interval, say 1 centimeter equals 10 meters, figure 9. Thus, the vertical scale will be 1 to 1000. Note that the horizontal scale of the map is 1 to 20,000. 6. From the marked intersection points of the contour lines on the graph paper, erect upward faint vertical lines with their heights corresponding to their elevation values and mark their ends. Figure 10. You may then erase the faint vertical lines. Figure 11. 7. Instead of the preceding step, you may lay the paper edge on the graph paper, then moves it upward while keeping it horizontal, and mark the locations of the contour intersections according to their elevation values. Figure 11. 8. Join adjacent points with a smooth line. On each side of the profile, extend the lines from the lateral points to the end of the profile without changing their slopes. Adjacent points of similar values are joined by extending the profile lines from both sides until they meet to form either a hill or a depression. Figure 12. This is the end of part 2. Computer drawing of topographic maps will be illustrated in part 3. So see you in part 3. Assalamu alaikum wa rahmatullah.